Hi and welcome. My name's Roger Webb. I'm the Director of the UK National Ion Beam Centre and the Director of the Ion Beam Centre at the University of Surrey. I'll give you a short introduction into the UK National Ion Beam Centre, what it does, and maybe how it might be able to help you in your research going forward. So the UK National Ion Beam Centre is a collaboration between three universities: the University of Manchester, the University of Huddersfield and the University of Surrey. The University of Manchester facility is at the Dalton Cumbrian Institute up near Windscale, so not actually in Manchester. The University of Huddersfield houses two facilities. There's the Miami in situ TEM facility and the medium energy ion scattering facility, both in the same department but slightly differently located. And the University of Surrey Ion Beam Centre has been a centre for microelectronics work since about the late 1970s, and has in situ three accelerators, and we'll talk more about all of these as we go through. So as we said, there's the UK National Ion Beam Centre consists of three facilities, one at Surrey, one at Huddersfield and one at Manchester, and there's just some pictures to look at of those facilities here at the moment. So what's so great about an ion beam anyway? Well, it's the charge. The charge on the ion allows us to do many things with the beam of charged particles. We can move them around in an electrostatic field, and we can move them around in a magnetic field. Particularly in an electrostatic field, it allows us to scan the beam across a large surface area, which means we can ensure relatively high uniformity of doping or of irradiation from the beam itself, which is and it allows us to manipulate that beam and move it into places where we want it. So electrostatically we have control over the beam, much the same way as with the old cathode ray tube. We could control an electron beam to make a very nice uniform TV picture. We can do the same with an ion beam and scan it over a sample to give a uniform coating or a uniform doping or a uniform introduction of material into something. The charge on the ion also allows us to collect the charge itself, so we can count effectively every single ion that comes into the material, so we have precise control over the quantity of material arriving at the surface. We can collect the ions and watch them literally come in one by one, and can control the absolute dose of material that's coming entering into the target material. The charge on the ion also allows us to specifically choose a specific isotopic mass in a magnetic field. So if we bend the beam in a magnetic field, we know that different masses bend with a different radius, so we can choose the exact isotope that we want by manipulating the magnetic field. That gives us absolute control on purity, so control on uniformity, quantity and purity in the system, as well as being able to manipulate and accelerate the particles to particular velocities. So we have uniform velocities, uniform coverage, we have precise control on quantity, and we have absolute control on purity. All of these features are kind of essential for many industries, in particular microelectronics one, which is where a lot of the early work has been dominant. So what is ion implantation? So ion implantation is a method of introducing elements into other materials in a non-equilibrium situation. A little movie that's about to run, and as soon as that runs I'll describe the way through. So what we have first of all is we generate ions in an ion source. We accelerate those or push those out of the ion source through a magnet to separate the masses, so we can get isotopic purity, as we said, and then we pass that through along a beam line through some slits to narrow the beam itself to make sure we select what we want. Then we accelerate it. We can bend it around magnets and focus it with quadrupole lenses, so that we arrive at an implant chamber where we can introduce that element into the material in wholesale. We can do that to change the properties, both the mechanical and the electrical properties and even the optical properties of materials. So we can harden metals, we can irradiate semiconductor devices to dope them, to make them electrically active. So that's the general principle behind ion implantation. If we do low doses between 10 to the 12, 10 to the 15 ions per square centimetre, then we're doing implantation with a distributed dopant. If we make our doses much higher, up to the 10 to the 15 to 10 to the 18 ions per square centimetre, then we're introducing enough material into the system to create new compounds. So if we put that 10 to the 18 oxygen ions into silicon, for example, we'll produce a buried oxide layer and buried silicon dioxide layer. So we can produce these insulating structures with a pure silicon layer above, so we can introduce a completely insulating layer below a normal silicon device itself. And if we do similarly with nitrogen in a metal, we can nitride the metal to make it to change its mechanical properties, to make it harder effectively. That's not always the best way to do it with directed ion implantation for such high doses. Such high doses are quite slow to produce with ion implantation. It's probably better to do those with some kind of plasma system. But ion implantation, because of its purity, gives you an ability to do research rather than just a little bit of almost bucket chemistry. So you know precisely what it is that you're putting into something. So from a research angle, it's quite useful, whereas for a production system, you hope you've done all that research and you don't need to do anything quite such purity because you already understand how it all works. So ion irradiation is subtly different from ion implantation, because in ion irradiation is irradiating a material with our ion beam, but in this case we're more interested in the damage that's being created, because the damage can affect the properties of materials as well, particularly in materials that are irradiated for a long period of time. The diagram at the bottom right there shows how a material can swell due to the damage that's created in from the irradiation. This is typically found in nuclear reactors that have been in operation for long periods of time. The nice thing about using an ion beam is you can accelerate those effects, and instead of having to wait 20, 30, 40, 50 years, you can actually generate the same effects in a matter of a few tens of hours of irradiation by a directed ion beam. So it's much easier to do research in that using a directed ion beam than it is actually a reactor. But the same argument is also used for ion irradiation in general, for looking at the performance of radiation detectors, how well they survive also under irradiation, and how they perform under irradiation, as well as biological systems in general. So ion irradiation, ion implantation, very similar to each other but subtly different. So we can also use ion beams to analyse materials as well. There's a raft of ion beam analysis techniques which utilise the outcomes of fast-moving charged MEV ions. So we look at the backscattered particles, we do Rutherford backscattering. If we look at the X-rays that are generated from the interaction of the particles with the surface, then we're doing particle-induced X-ray emission, PIXI. We can also look at the gamma rays that might be emitted when using the nuclear reactions effectively that are occurring due to the fast-moving particles in the material. That's particle-induced gamma emission or nuclear reactions analysis. We can also look at the scattered light that comes from the interaction of the particles using ion beam induced luminescence. We can use the sputtered molecular material that comes off due to the interaction with the electronic energy loss of the material, and we can look at the SIMS, secondary ion mass spectrometry, effectively the ions on the surface. We can monitor the charge at different points in the surface, doing a technique known as IBIC, ion beam induced charge. We can pass the beam right the way through and look at the energy loss, doing effectively a form of scanning transmission ion microscopy. And we're going to tilt the sample and recoil out particles in the material as well, and do what's known as elastic recoil detection analysis, or forward look at forward recoil of target atoms. It's particularly good for light ion profiling, particularly hydrogen. It's one of the things it's extremely good at. So the facilities that exist at the UK National Ion Beam Centre that you can get access to are at the University of Huddersfield, University of Manchester and the University of Surrey. So at Huddersfield there's the Miami facility, which effectively is a in situ TEM microscope with a dual beam implanter, so 2 ion implanters which converge in a Joule TEM, so you can actually watch the radiation damage being created live as the implantation, as the irradiation takes place. So that's one facility. Also at Huddersfield is the MAIS facility, the Medium Energy Ion Scattering Facility, which is a 50 to 200 kV ion accelerator, which is used for scattering ions from surfaces, usually light ions. And there we're looking for the backscattered particles. We're looking at the high resolution depth profiles of the elements that make up the surface region of the material. The sample can be aligned into particular crystallographic directions so that you can channel the ions in perfect crystals, and therefore you can look at defects that are created by other means, either irradiation, implantation, or other surface treatments. So you can look at the damage that's introduced in the surface region as well using the channeling technique. At the University of Manchester Dalton Institute in Cumbria, we have a nuclear user facility which involves a 5 million volt tandem accelerator and a 2.5 MV single-ended accelerator. These are used largely for radiation damage studies and radiation chemistry studies. There are a number of beam lines which in some cases converge from both accelerators to allow you dual irradiation, so irradiation of two energetic beams simultaneously, which is useful for nuclear damage studies. These are available. The Dalton Institute also has available to it a beamline which goes into a hot cell to allow for high damage rate studies where nuclear activation takes place, so when materials become effectively irradiated and radiated materials effectively become hot, so that they're not good to have in an open lab. So the hot cell allows you to irradiate to the point of activation of the material. They also have a beamline which is available for some of the beam analysis activities, particularly the PIXI RBS nuclear reactions analysis and elastic recoil detection. Some of their facilities also allow high temperature and high pressure control, as well as having Raman spectroscopy available. The Surrey Ion Beam Centre has 3 accelerators currently, 2 of which are used for materials modification, ion implantation, and 1 of which is used for analysis. The 2 that are used for materials modification, ion implantation, are specifically a high energy implanter, which runs from about 400 kV to 2 million volts, and a high current implanter which runs from about 2 kV up to around 200 kV. With doubly charged particles we can overlap the 200 to 400 kV between the 2 machines, and also give availability of something like 4 MeV implanted ions with doubly charged particles. So it gives us a reasonable energy range and a beam current of around, up to a maximum of around 10 milliamps for some ions. We're able to irradiate over sample sizes ranging from a few millimeters squared, as long as we can mount it, all the way up to around about 40 centimeters square. We can also run implants hot, so up to about 700 centigrade, or cold around about 10 Kelvin. The sample chambers themselves are situated in a class 100 clean room for semiconductor work. The picture on the right there shows the ions that have been implanted. So pretty much everything in the periodic table at some point or another we've implanted for somebody somewhere. There are 2 ions in orange that we've never done, which is scandium and lutetium. The ones in red are ones we don't normally do, won't normally do because of the radioactivity that's involved in the ions to generate them. So they're too messy to actually generate in our facilities. So keep away from the red ones. The green ones and the orange ones are generally available to be used by anybody who wants to use them. Surrey Ion Beam Centre also has a 2 MeV tandem accelerator, which is used for ion beam analysis largely. So it's will use techniques such as rutherford backscattering, elastic recoil detection, particle-induced X-ray emission, particle-induced gamma-ray emission, nuclear reactions analysis, ion beam-induced luminescence, ion beam-induced charge, and MEV sims as well. All of the techniques, all of the IBA techniques that we mentioned earlier. We also can do channeling spectroscopy. We have a multiple axis goniometer which allows us to line the beam to the crystallographic directions of the target, which allows us to look for channeling spectroscopy for damage analysis of crystalline materials. That goniometer is fully automated to allow us to do fully automated collection and analysis. We also have an external beam for vacuum sensitive samples, which means we can take the beam out through a thin silicon nitride window and perform the analysis actually in full ambient conditions. The beam travels about 7 centimeters in air potentially. You obviously want to get a little bit closer than that, but it gives us a fair bit of room to manipulate samples in front of the beam line. The beam spot size is typically, in that case, a few microns, typically 10 microns, but with good luck and everything else, we can possibly get that down to about 2 microns. In vacuum, we have a horizontal nanobeam which can give us a spatial resolution of around 500 nanometers at best, and typically around 1 to 2 nanometers, 1 to 2 microns, excuse me. There is also possibility to use that line for implantation and irradiation, although the majority of the time we use the other accelerators for implantation and irradiation. So the Surrey Ion Beam Centre also has recently commissioned deterministic single ion implanter, Simple. In fact, it has 2 of them, Simple 1 and a Simple 2. Simple 1 is has a range of different ion species, from silicon through to manganese, selenium, erbium, bismuth, phosphorus, germanium potentially. It's based around a focused ion beam, a FIB type system with a liquid metal ion source. So ion species are not all that easy sometimes to generate. But we also have another simple with a slightly different ion source on it, Simple 2, which has a dual plasmatron source, which allows us to produce gaseous species like nitrogen, oxygen, helium, neon, argon, potentially carbon as well through CO2. So these give us a capability to actually implant single ions, one at a time, literally, with a spatial resolution of around 20 nanometers in the case of Simple 1, and around 40 to 50 nanometers in the case of Simple 2. So I'll give you a little bit more information about the ion beam analysis and what its particular capabilities are. So, what's PIXI? PIXI is particle-induced X-ray emission, and basically it occurs when an ion beam causes ionization of the target atoms that it passes. As the ion passes elements in the material, it ionizes, potentially ionize some of those target atoms. In other words, it removes an electron, which is shown in the picture to the left there, and this leaves a vacancy in one of the electron shells, and an electron from an outer electron shell jumps down to fill the gap, and in so doing it generates an X-ray to lose energy. And that X-ray is characteristic of the difference in the energy levels, and because different atoms have different numbers of protons. The spacing of the energy levels for different atoms is different, and therefore the X-ray energy is characteristic of the element from which that X-ray originated. So because the ion, as it penetrates through the material, passes lots and lots of different atoms, it potentially generates a large number of X-rays from all of the different atoms that it sees on the way through, and therefore is quite characteristic of and can identify many of the trace elements that are inside the sample, as not just the bulk of the elements, but the trace elements that are in there as well. So it's very useful for finding low levels of trace elements in materials. Why use PIXI? Well, PIXI is available to detect elements in the periodic table from about sodium up to uranium with the detectors we currently use. If you're interested in elements below sodium, so sodium, lithium, boron and fluorine, there are nuclear reaction techniques and particle-induced gamma irradiation techniques that can be used to supplement these. So sensitivity is in the ppm level for most elements. And the figure to the right shows a comparison between PIXI and SEM-EDX. So it's a very analogous system, apart from with an SEM, of course, you're using an electron beam initially to produce those characteristic X-rays as opposed to a proton. And because you're using an electron beam in an SEM, you have a Bremsstrahlung background, which is shown in the yellow on the picture to the right there, and that means some of your trace elements get lost. So the sensitivity of SEM-EDX is low by comparison to the sensitivity of PIXI. Because we're using a proton, there's no Bremsstrahlung from the initiating beam itself. So we have much greater sensitivity in PIXI than there is available in SEM-EDX. Also, the beauty of PIXI is that we can carry out the analysis in air. We don't have to be in vacuum. Like I said before, our beam can come out of the vacuum system, travel about 7 centimeters in air. So we can actually extract the beam in air and do the full PIXI analysis in air. So it allows non-destructive analysis of large and potentially vacuum sensitive samples. And there's also usually no need for sample preparation. The penetration depth of the proton beam is several microns. PIXI analysis gives absolute quantification potentially, so there's no real need to compare to standards. The accuracy of the technique is around a few %, and PIXI analysis is usually simultaneously done with backscattered particle spectrum as well, the RBS spectrum. This gives us complementary information that we can use to determine depth profiles of the major elements. So what about Rutherford backscattering? Well, Rutherford backscattering can tell us the information about the compositional state of the sample. So it tells us which atoms are present and where they are in the sample, how deep they are into the material. So we use an ion beam from an accelerator rather than an alpha source that Rutherford used back in 1911. So things have progressed a little bit. We detect the particle velocities when they come back, their kinetic energy, and we know the mass of the particle we sent in. We know the velocity of the particle we sent in by detecting the velocity of the particle coming back. Its kinetic energy, its mass hasn't changed, so we know we can find out what the mass of the particle was that we hit. So some useful information from the backscattered signal tells us precisely the masses. And because the particle loses energy slowly as it goes into the material through collisions with electrons, we can get accurately how deep into the material it was when it hit the atom that it hit coming back. So there's some useful information that comes back from Rutherford backscattering. It tells us what the atoms are, the major constituents of the target material, and it tells us where and how well distributed those particles are in the material. With nuclear reactions analysis or particle-induced X-ray gamma ray emission, we're now looking at what happens when there's a nuclear reaction that takes place, a resonant reaction, where the helium or proton that comes in close to the nucleus actually involves the breakup of that nucleus into different components, and that can give rise to either gamma ray emission or different reaction products. We detect these reaction products either as fast protons, fast alpha particles, or just the gamma rays. And we can detect those and determine again potentially how deep something is from the energy loss of those various reaction products, or by energy loss of the particle that goes as it goes into the material, and tells us a little bit about not just what's there, but how deep into the material it is as well. With elastic recoil detection analysis, what we're doing now is using usually a heavier ion beam, so either helium or even higher up to oxygen or chlorine even, to actually recoil out elements actually in the surface region of the sample. So we now come in at glancing angle to the surface with our detector at glancing angle as well, and we now detect the atoms that are recoiled out of the surface layer by that heavier ion beam. This is particularly useful for looking at things like hydrogen and helium in the surface layers of materials, which are hard to analyse and find otherwise. As the MEV ion beam penetrates through a material, if the material is an insulator, particularly an organic insulator to boot, then the chances are that some of the material from the surface region can be sputtered. We can look at the secondary ions that are sputtered by that probing beam to determine the mass of those molecules or ions that are actually on the surface of the material. So in organic systems, particularly, we can look at the molecular weight of the organic material that's sputtered from the surface. We can do that in the usual time of flight mass spectrometry system, either in vacuum or in an external beam arrangement. External beam arrangement is something that would be nice if it worked well, but doesn't tend to work so well because of the ambient background is usually fairly high. So this summer we've got two new instruments coming into the lab. By the end of the summer we should have the new instruments up and running. So the first one is a high resolution X-ray detector, which should be available for use somewhere around the back end of this year. And the resolution of this detector is much greater than the current resolution of our detectors. If you look at this is a simulation of what our current detector looks like for a range of heavy metals. Our current energy resolution is about 130 eV for the X-rays, and we can barely distinguish the various different peaks from different heavy metals here. So we have to work usually by knowing which heavy metals we actually have to give us an idea of what's available. So with a new detector around about 2 electron volt energy resolution, we will be able to separate all of the heavy metals very distinctly, so we'll have a much better resolution for looking at specific elements in the material. We're looking forward to having that one on our books soon. And the second item coming on also around about the same time will be the high resolution elastic recoil detection system, which will give us a much higher resolution for our elastic recoil detection system, using heavier ions to look at not just hydrogen and helium, but potentially many atoms up to and around chlorine in mass. So I'm looking forward to seeing that one too. So we have a much better depth analysis for light elements from the new system. So just finally, we do have a couple of other little useful focused ion beam pieces of equipment in the centre. We also have semiconductor annealing equipment, some standard electrical characterisation and mapping facilities, all within our Class 100 clean room. and just for completeness we operate under an ISO 9001 certification. So if you have any thoughts about what you might be able to do with such equipment, please get in touch. We hope to hear from you or see you soon.